In this video, we're looking at example 8 in section 5.3. All right, so we're going to use the substitution rule to evaluate the integral of sine of x over cosine squared x. So again, the number one thing, or the first thing we have to do is to find the u. And this can be difficult. And with more experience, you'll get more comfortable choosing the u's. But sometimes the experience we need to take are attempts for u's that don't work out. Because in this can give us some insight to what u's do work out. So with that said, let's just try something for u. So we have a sine of x and a cosine x. So maybe we think that we want to have u be sine of x. Keep it simple, keep it on the numerator. Cool. So I'm going to write attempt 1. Because we might have to revise this u. That's okay. We shouldn't be totally married to our u. We need to choose the u that will work for us. All right, so let's let u equal sine of x dx. Nope, no dx, sine of x. So then du with respect to x is going to be cosine of x. Now we can move that dx over. So now if we substitute in, we get the integral of u. We still have a cosine squared x on the denominator. So we need to try to make sense of how to find a du here. So we cannot put a du in the denominator. It's common, it's tempting to want to do that, but we need to have our integral in the form of some function with a du on top. And that's just standard mathematics convention. Just we can't have a du in the denominator. It doesn't make sense for how a integral is written. Recall, integrals are like adding up area, where we're taking a height times a width, and we can't take a height divided by a width. It just doesn't make sense. Okay, so what we see here is that we could, I don't really know how we can make sense of this, because we can't find, we could have, let's say we could put in a du there. So the integral of u du, that would introduce an extra cosine. So we'd have to divide by an extra cosine to get that cosine to cancel. So in that sense, we would be able to get dx to cancel out. But then we still have cosine squared x that we need to take care of, which we can't really make this u, move this u around anymore to find a cosine. I mean, we could try some trig stuff, like we could go, well, we know cosine squared x plus sine squared x equals 1. So we could say, well, this would be cosine squared x plus u squared equals 1. So we could say cosine squared x equals 1 minus u squared. So I could substitute 1 minus u squared for cosine squared. Then we have a u in the numerator and denominator, and it just gets way more complicated, right? So at this point, once you've done some thinking and work and massaging and it just doesn't work out, we just say, okay, that was a nice attempt. Let's try another attempt for u. Okay, let's do it. New attempt. So here is fresh attempt 2. So last time we used sine, so let's use cosine. So let's let u equal cosine of x. So now du would become negative sine of x dx. And now if we look back at our integral, we can identify some u's and du's here fairly quickly. So that's a sign that we are on the right track. So we see that we have the u squared in the denominator. And then as soon as we take that du, we see it appear here, just with a different sign. So that means if I negated here, if I added a negative to both sides, that would change that sign of it, negative sine of x, to a positive sine x. Okay, we're looking like we're in business. So that means our integral, I'll just write it out so we have it on the same screen, of sine x cosine squared x dx. We see that we can find the u in the denominator. We just need to square it. And we see that we have a negative du in the numerator. So then this just becomes the integral of negative du over u squared, which is equal to negative integral of 1 over u squared du. Okay, not looking too bad now. Now we can recognize this as a function where we can compute its antiderivative. So that would just be using that reverse power rule. So keep in mind 1 over u squared is equal to u to the negative 2. So we add 1 to the exponent and then divide by that new exponent. So we divide by negative 1. So that would be negative u to the negative 1 over negative 1 plus c. So now if we combine our negatives here, those two negatives cancel out, and we're just left with 1 over u, or u to the negative 1, plus c. All right, are we finished? Not quite. We were given an integral with x's, so we need to return an antiderivative with x's. So now we substitute back in for u. So this is equal to, u was cosine x, this is equal to 1 over cosine x plus c. So now we can box that up as our final solution. So now let's look at example 9 in section 5.3. The more you do these, the more fun they become, because it's kind of a challenge to find u at first, but once you find the u, it just works out so nice. All right, so here we're evaluating from 1 to e, so we're having a definite integral, ln of x over 2x dx. So we could do a little trial and error, and if you do that, you'll see that if we let u, so I should get out of shape mode, if we let u equal ln of x, then recall the derivative of u then, with respect to x, would be 1 over x. So we can bring that x over. So here, we're looking pretty good. So we can see that we have a u then in the numerator, and then this dx over x becomes our du. So that means that this is equivalent to the integral where x equals 1 to e of u du over 2. So we still need that division by 2. We could either introduce that here, divide both sides by 2 to really see that dx over 2x, or we can just be mindful of that when we're doing the substitution, that if we don't have something pop out in the du, then we need to make sure we include it in our function still, or in our integral. Okay, and again, this is equal to x equals. So again, at this point, I like to go ahead and change these bounds to be u's. So if x equals e, then u is equal to ln of e. So ln, natural log, tells us what we need to raise the base of e to in order to get what's inside. So what do we need to raise e to in order to get e? Well, we would just need to raise it to 1. So ln of e is just 1. Now, if x is equal to 1, then u is equal to the ln of 1. So that answer, whatever ln of 1 is the exponent on e to get 1. So that would just be 0. So we can change these bounds right away. So when x is e, u is 1. So we just go u to 1. And when x is 1, u is 0. So then u would be equal to 0. Now we have u du over 2. All right, this just gets simpler and simpler, right? Isn't it so satisfying how it just like becomes so nice and straightforward here? So now we can bring that 1/2 out. We have the integral from u is 0 to u is 1 of u du. All right, now we got this. What's an antiderivative of u? Antiderivative of u is just u squared over 2. So we're evaluating that at 0 and 1. So we can even combine this to be a 4 in the denominator. So I'll do that on the next step. So then this just becomes equal to 1 over 4. I'm just going to bring that out. And then I'm evaluating at 1. So I have 1 squared minus evaluating at 0, 0 squared. So that just becomes 1/4 times 1, which is just 1/4. Awesome. Super satisfying, right? Not too bad. Nice. Okay, I understand that we are just learning this. So at first, this can seem kind of a scary process. But again, the more videos we look at, the more problems we practice, the more we work together, the more enjoyable, the more straightforward, the more simple it will be. All right, thanks for watching.